So let's take a look at the conclusions from day 2 of our force lab number 2. In order to earn your done stamp for this activity, you must show me these conclusions done correctly, and you must show on your paper the correct free body diagrams for each one of the situations that we experimented with. Your free body diagrams might be close to being correct, but there's probably some things that you're missing. So, just to be clear, answer the conclusions and have correct free body diagrams to show me, and I will be looking. All right, first of all, in situation number 1, I had you pull on the block and try to get it to move, but at the same time, one of your group members was pulling up with a force of 2 newtons. Let's talk about the free body diagram here. So we had a weight of the newtons. Your brick might have been different than this, might have been 15, whatever. This is about the right weight. So we have a weight going down. You applied a force to try to get it to move, and you also pulled up with a force of 2 newtons. Well, let's finish this. You know that if the brick were stationary, you'd have a force going down of 16, and you would have a force going up of 16. That's that normal force. But you are pulling up with a force of 2 newtons. Remember, the forces going up and the forces going down must be balanced because the brick isn't moving up or down. So if you were pulling up with a force of 2 newtons, the normal force in this case must be 14 because it has to balance out the weight going down. Your applied force was different for different people, but you would also have had a frictional force going the other way. And I'm going to make up a number here. Let's say that you had to apply, make up a number, 5 newtons of force to get the brick moving. Once again, your answers may vary. Now, in the second part, I had you pull up with an applied force of 5. Well, the weight is still 16, so the total upward force also still has to be 16, which means now the normal force is now 11. You applied a force this direction, which was overcoming the friction that was going the other direction. And once again, I'll make up a number. Let's say it was about 3 newtons. Once again, your mileage might vary depending upon your brick. Finally, I had you pull up with an applied force of 10 newtons. Well, the up and down forces still have to be balanced. If you're applying 10 up and it's 16 down, now the normal force is only 6 newtons. Your partner applied a force this way, which overcame the friction going the other direction, and now this might have been down to something like 1 newton. So for answering question 1, describe the trend in the amount of frictional force from situation 1 to 2 to 3. The frictional force got less. It decreased every time as we went that way. And the only difference was same brick, same surface, everything was the same, but you were changing how much you were lifting up on the brick. So what explains that trend? If you notice, now the normal force is less. It was 14. You pull up a little bit more. Now the normal force was 11. Now the normal force is only 6. Remember that the force of friction is directly related to the normal force. So if this goes down, the amount of frictional force also goes down. And you made this go down by pulling up. This is why, like when you're trying to push something across the floor, like a heavy couch, it's easier if you lift up on the couch a little bit. If you lift up on the couch as you're trying to move it, you're actually decreasing the frictional force because you're decreasing the normal force. So now let's look at this situation here. And here's where the free body diagrams get to be a little bit trickier, get to be a little bit more complex. So we still have a weight, and let's say it's still 16 newtons. And you were pulling, you made an applied force to now pull the brick up the ramp as opposed to pulling it horizontal. Well, let's look at all the other forces that are in play here. There is still a downward force of 16. It is contacting this surface. And we know that there is a normal force that acts against the surface of contact at 90 degrees. So there's my normal force. Now let's take a look at this free body diagram though. If there is a force going this way, we know it's 90 degrees to the surface of contact. There must be an equal and opposite force going the other direction. Because if I don't show that blue force there, it looks like, hey, that's the only force going that direction, and that brick is not accelerating off of the ramp. We also have a force that pulls down the ramp, because we know that at some point the brick would slide down the ramp. Well, these two forces here are components of the weight, because it's the weight that pulls the block onto the ramp. It's also a portion of the weight that pulls the block down the ramp. Because these are components of the weight force, they are generally given the names parallel and perpendicular weight. We're going to go parallel weight, perpendicular weight. This is the portion of the weight that acts perpendicular to the surface. This is the component of the weight that acts parallel to the surface of contact. Now, when it's horizontal, the weight is just the weight. There is no parallel and perpendicular weight because the weight is still at 90 degrees to the surface. This perpendicular weight is found using that. The parallel weight is found using that. This is the force of the weight that pulls it down the ramp. This is the component of the force of the weight that pulls it or keeps it on the ramp. The normal force, therefore, has to be equal and opposite to that because it's not flying off the ramp. So typically, we know the normal force is found by using that mg cosine of theta. Now let's talk about the force it took to pull this up the ramp. This was more than what it was to drag it horizontally, because now, why was the force needed to pull it up so much greater? Think of the force here to move it horizontally. All you have to overcome is friction. So you only got to provide enough force to overcome friction. But when you're on the ramp, you still have friction. If you're pulling this way, we still have a frictional force that works against you. But there's also that parallel weight working against you. So now, in order to get the block moving, you have to overcome two forces as opposed to just the force of friction. And that's why the force needed to pull up the ramp is so much more, because you now have to overcome not just friction, but also the parallel weight. Now, in this situation, I asked you to pull down the ramp. And the free body diagram would be the same as up here, except we're flipping this force over. We're pulling down instead of up. What that does is it changes my frictional force, because remember, the frictional force is going to work opposite the motion. Now, this force was much less than this force. And the reason is because now the parallel weight, the force down the ramp, is actually working with you. So the only force you have to overcome is friction, and this mg sine of theta, this parallel weight, actually works to help you pull it down. So to summarize, why was the frictional force in the second part of situation so much less than when the ramp was horizontal? Because now